Thank you so much, everyone, for bearing with us till the almost very end of session 2. So right now we'll have a long discussion session for approximately 22, 23 minutes. And in this discussion session, we just want to sort of ask some questions and discuss together about the big problems in cosmology and about these sort of inference, ML inference methods. So the first question that was asked from the audience comes from table number 9. Where's table number 9? Peter? If you could raise your hand, I could see you. Yeah, I'm going to be blind. Thank you. So you asked this question. SBI NP or NP requires very accurate noise models. How hard is it to train these? Do we have good diagnostics? Would you like to tell us a bit about it?
So this is a part of a discussion that was ongoing, and I tried to summarize this. But the main underlying question is, in SPI you have to be able to simulate your data, including the noises. And if you use a wrong noise model, then the results are incorrect, and you have no guidance as to how bad this problem gets. So there's no bound on the error that you can construct with neural posteriors, for instance. So the question is, how hard is it to make a better noise model? And we've seen examples in Lawrence's case, and there was we've discussed the question of was it difficult to make a James Webb noise model? But sort of a second, and that's the other part of that question is, when do we know when the noise model is good enough in order to allow the quality of inference in terms of parameters that we want to get out of this to be achieved? So at what point are we happy?
We are going to do things a bit differently now, so we're opening the room for discussion. Any comments on that from the room? Yes.
So we have so for us, like in our case, where we train noise models, saying like on James Webb's darks. So when we do our training, we always keep like a test set basically of darks that we've never seen, and then we can use 2 sample tests on the samples that we generate from our noise model versus like real darks that we've never seen to test the null hypothesis that they come from the same underlying distribution basically at the pixel level. And then when we are happy that the 2 are indistinguishable from each other statistically, then that's what we use to analyze data. So it's not like you're still limited by sample variance, but it's pretty much as good as it gets because it doesn't rely on like compressing those those noise samples down to lower dimensional latent spaces, because typically that's very difficult to do well specifically for noise, because typically those embeddings are invariant to noise. And so that's why it was like specifically important to us to develop methods that would work at the pixel level without any compression. So that's why we use PQMath.
This is like a pyramid.
Just a quick. Just to clarify this, that 2-sample analysis will actually help us to understand whether the assumed noise model is correct or wrong, but how it will lead to build a more realistic noise model. We are not interested in testing. We want to build more realistic noise models starting from a Gaussian. I think statistical hypothesis testing or p-value cannot get there. You have to start from Gaussian model and you have to change that model. Just testing will just going to accept or reject that, but will not tell you how to build the realistic model. So the question is not hypothesis testing. The question is, how can we start with a Gaussian model and build better model?
Totally agreed. I think I was mainly unclear what I meant. The question isn't should we build a better noise model. If we can, we definitely should. The question is, if we have a noise model as is, and this is our best effort, right? Would we know that it is good enough in order to achieve the cosmological results or any other kind of SPI results that we want to achieve? And that was sort of what I meant. It's not that when it's not the. And that is a decision, right? Are you going to accept the results given the best quality noise model that you can have? Is that good enough? And you need to make a decision on that point at some point.
Any more questions? We have 2 more very spicy questions. So Okay, and the tiramisu is waiting, so just as a nice thing afterwards. All right, cosmology analysis. Okay, so we have, I think, a question from the field table. I'm gonna go next to field. All right, cosmology analysis scaled up for LSST might necessitate approximate inference, variation inference with NDP, for example. Does it matter if we don't feed the data on any individual object if we still get the same if we still get the cosmology correct? There's a part 2. And how will we know we have the cosmology right if we don't fit the image data? Phil, do you wanna say more about this?
This is really was coming out of a conversation we had with Laurence, but it's sort of me on the psychiatrist's couch worrying about how things are going to work. I mean, we've noticed in with the MPE that it's this approximate inference where we don't fit the data. We make predictions that are pretty good, but they're not actually fitting the data. But when we do our verification tests, we seem to recover the global cosmological parameters. So we're feeling somewhat comfortable with that, but there's this nagging doubt that, you know, if we're not actually fitting the data down to the noise, can we believe the results at the end? So I was wondering if anyone else is in the same uncomfortable boat as us. Any comments on how to think about this?
Yeah, so I agree with the discomfort because as we talked about, in some of these methods, we don't know what it is doing to actually get the results. We know it's not doing what Laurence is doing, which is actually, you know, minimizing the residuals for each image. We know it's somehow doing some approximate things to get the right posteriors for the parameters, but we don't. My discomfort is, yeah, not only is it, you know, on image by image basis, you know, it's not as good as, you know, a graduate student could do, but I also don't know what it's actually decided to do. And so that's which is a general issue with machine learning for me, but yeah.
So Josh has a whole other layer of angst about this.
Any more angst in the room about this question or any hope? One question I kind of have about bias amplification, maybe Phil. You know, I've seen in some proposals that folks want to build emulators to predict from something, and I don't think I've seen the discussion of bias being, how to account for bias amplification through this emulation being part of an inference pipeline. Do you have any sort of angst about that?
I think we should hear from someone else. Someone else's psychological problem.
Yeah.
So, you know, I think emulators can be extremely powerful, but they're often trained on limited data sets. And, you know, simulations can be extraordinarily expensive to run. That's why we build emulators to begin with. But they can be incomplete in the physics that they're treating. And I do worry a lot, and I've seen this myself, where with a restricted set of simulations, you might say everything's hunky-dory, we actually fit the parameters that we think we should be fitting. But as soon as you allow for some other confounding physical effect, that's no longer the case, or some other model could fit the data just as well and look like, masquerade as, something that would be in the emulator's training set. So I think we have to, you know, not abandon the approach of doing actual physical simulations, but then leverage, you know, that data set that we generate in those simulations to build emulators to answer other questions much more rapidly and effectively.
Any thought? I saw.
Yeah, just to increase the angst from Phil, that even in a very, like, kind of like the basic or like the fiducial way we do cosmology right now, for instance, with weak lensing, getting the data vector and doing the MCMC from there. Even this, we also worry about, do we get the correct cosmology? I mean, and it's already a challenge. And so we rely on simulated analysis, being blinded, and I think SBI has to do, has a lot to do in that direction as well, developing ways to be extremely robust, proving that the approach is unbiased and things like that.
Any response? Okay, and then for the last question of the session, comes from table 14. This question is quite similar to the one that Phil posed, so it's about model misspecification. So Risa mentioned, in Astro, our models are almost always misspecified, and our label data are almost always biased. We heard about great techniques to deal with all of this. Where are these already good enough? Where do they need much more work? Risa?
I don't have an answer to this question. It's an honest question, but I'm very angsty about it, about both of these problems separately and together. I think, as Brant mentions, like we're not close to being able to simulate the universe at the precision we measure it. I worry about that all the time. I mean, if we were, we would have solved everything. And then we have this very, very common problem in astronomy. Sebastian and I spent a few hours talking about this yesterday, that our labeled data is always biased, and most of the time we don't even understand those biases very well. And so that's a big challenge. So I think we need, when I think about, we're talking more about foundation models tomorrow, but it's definitely something I think about a lot in that space, how we understand what the embedding space is, et cetera. So I don't have an answer, but maybe Laurence does.
Any?
Do I have to say something? No, you don't. Yes, it's a question. And I haven't solved the universe either.
Okay, great.
Do you think this will ever be solvable? Do you think that we'll ever be able to actually take all of this bias of the label data into account?
Laurence, I know you haven't solved the universe either, but could you say anything more about where you think where you think we can correct for these biases and where it's hard? That's kind of what I.
So, I think the way, it's not just, I forgot to mention that, I totally wanted to give a shout out to Peter and Benjamin and also Francois, but I just forgot because I was stressed out when I was talking. But they also are doing the same thing about, correcting for misspecified priors, and in a way that, it converges to something that works really. Also, Sebastian, you're doing that too. So that, I think that's a problem that's it is very data expensive. It is not computationally cheap either, but if you really care about getting things that are really in distribution from the point of view of the prior, it's something that can be done. And so I think from the point of view of prior misspecification, that's a problem that we can solve. I think that there's a way to phrase model misspecification within the same framework. So I think that when you have a model that's misspecified, it's because you have a prior over, that's implicit in the way you've parameterized your forward model. And so you're basically putting zero prior over the space where reality lives. And that's it can be phrased in the form of prior misspecification as well. And so I think that to some extent, the same technique can be applied to model misspecification. I think it's a lot harder there because it's hard to figure out what's the right inductive bias you want to have so that you don't start just maximizing your likelihood, and fitting everything to noise, basically. But I think there's more progress that can be made, but there's something that could be learned in that space.
Along the same ways, I think there's a possibility that we use the techniques of updating the priors to absorb some of the model misspecification, but you cannot get all of the model misspecification out. There's blind spots where your model is so wrong that you can't get your prior to get there. But it is quite feasible that we use the flexibility of these priors, specifically if they're high dimensional and constrained by a lot of data, to absorb some of the misspecification that exists in our forward models. And then constraining them by data.
Yeah, exactly.
Okay.
That's what I meant. Basically empirically learning the parts of your model you're missing.
Yeah.
Right?
that goes even beyond that, right? So that has the chance of capturing those things. You may not necessarily understand why it's happening, but you at least have a mechanism to see it, yeah.
Any more comments? Dalia?
I'm slightly outside of this field, so I want to ask a more general question of the people here who care about precision cosmology and any type of very advanced inference framework. So in the context of SBI, 2 years from now, if a result comes out that suggests a tension, significant tension with a well-accepted theory, like the standard model, what type of tests and sanity checks we as a community want to do in the next 2 years to understand whether this is a result we want to trust or not? What would you like to see happening in the next 2 years to test this?
Well, okay, if something's like, going against the standard model of particle physics, that probably means that you're discovering new particles, or you're measuring some cross-section that you've computed, and it's just miles away from what the standard model prediction is, and you can compute a bunch of loop diagrams that say, okay, all these other particles should exist, and so forth. And so what you're going to end up with there is basically a bunch of predictions about there should be this particle, there should be this particle. There's going to be a whole spectrum of other predictions that you can extract from the standard model of particle physics about other effects you should see, and so forth. And it's really hard to wiggle something in the standard model of particle physics and not have crap wiggle all over in a bunch of other places. Whereas I think in WOA, that's directly challenging the standard model of cosmology, and it's not really affecting things in a bunch of different places. And so there's some there's some intrinsic difference there. I see Risa shaking her head about WOA not challenging other aspects of.
Yeah, one other thing I would say to answer that question is I would ask, where is the information coming from? So for instance, if it's field level LSBI, is it coming from small scales? Is it coming from like the bispectrum? And then I would ask to do actually the analysis just using some statistics that would represent that. So I think actually that's what I found the most interesting about SBI is you can ask the sort of question is, where is the information contained? And then, yes, I agree, like even right now, even like a strong evidence for dynamical dark energy, we are like always asking what other probes are doing, we need to measure better, etc. Like, yeah.
Oh my God.
I was going to say something similar in the sense that, at least on the cosmology side, when you have something like dynamical dark energy, you need to understand what the other predictions of dynamical dark energy that have been ignored up until now are, so we can go and verify them. But in the case of the standard model, like the muon G-2 measurement, was telling people, oh, there's something missing, we just haven't done the calculation correctly. And then once people figured out the hadronic loop was wrong or something, then they got the right answer. And I think those are very different, alerts. When you see something unusual in those different fields, in astronomy, it's about, we don't yet know what the predictions of these changes are. We need to go and look them up. In particle physics, a lot of the time, my understanding is, oh, we've made a mistake somewhere. We have to go back and figure out where that mistake is. And that's because that model is so rigid and also extremely predictive in a way that we don't know what the predictions on the cosmology side are for some of these models.
Any response to that? That would be a very famous last words because we're entering the final. Yes? No? All right, then with that, I think we can end the session, and thank you so much. And the food is there, so please enjoy this and join us in 1 hour for the panel as well. Thank you.
Yeah, just want to emphasize, don't go away. There's great food and drink. Talk to each other. There's going to be a super wonderful panel in an hour right here. It'll be really, really interesting. We're going to, talk about the future of AI for science. Hope you guys will stick around. And it was super stimulating today. And hope to see you at the panel and tomorrow morning.